The reason why might not be clear at first, but it turns out that sampling is a surprisingly useful practical tool. So in this video, we'll talk about why sampling is so useful, and we'll talk about some pros and cons of sampling methods. First, why is sampling so powerful and useful? So why sampling? Well, the main reason is that it allows us to approximate expectations in a very easy, convenient way. And approximating expectations allows us to do things like estimate statistics. For example, if you were if you're doing some sort of financial analysis, you might be interested in how much money are you going to make, and that would be a statistic over some period of time, how much money you make, what your return is, and you could estimate that. That would be an expectation that you might estimate, or you might estimate, if you're in physics or something, I don't know, the length of time before some reaction occurs, something like that. So this is one application of expectations, and this is sort of the general thing, is estimating statistics, and some particular statistics are probabilities associated with the distribution, and so we can do things like posterior inference and I'll just put posterior inference in general. Computing probabilities. So those are just a couple types of things that we can do with expectations, in particular in statistics and machine learning, but this is in fact much more general, and we'll talk about that in a second. The other reason why you might do sampling, or at least one other reason that springs to my mind, is visualization of typical draws from a distribution that you're interested in. And this is particularly useful when you have some sort of very complex distribution and some sort of complicated things that are happening. Like, for example, if you had a model of the folding of a protein, and so you have some protein, and it folds in a super complicated way, and you'd like to draw samples from the probability distribution over the different foldings of the protein. And this is an extremely complicated thing, but it might help you to get some intuition into what's going on if you could at least draw samples. And then, maybe one thing that you would do is cluster the different samples that you get. That may be one application of this. Okay, so I said that I claimed that this sort of approximating expectations was a very general sort of thing. And why is that? I mean, you might think expectations, well, that's just a very sort of special thing. It's just the mean of a distribution. Why is that so general? Well, first thing maybe to note is that any probability is an expectation. Any probability is an expectation. I'll put E for expectation. And why is that? That's just because if we have the probability of, say some random variable x is in an event, is rather in a set A, the probability that x is in the set A, we can write as the expected value of the indicator function that x is in that set. So you can always take a probability and write it as the expected value of an indicator function. And therefore, anytime that you want to estimate a probability or approximate a probability, then you can formulate it in this way as approximating an expectation. And a little more generally, typically, the things which are hard to compute turn out to be things which are sums or integrals. So, it's not always the case, but many times, almost, a huge amount of times, I don't know if I could say the majority, but a very, very large number of times, things which are hard to compute, so approximation is needed for sums or integrals. Many times, the things which are hard to compute and therefore need to be approximated are sums or integrals. And any sum or integral can be represented as an expectation over some probability distribution. Well, that's a very general statement. Let me back off that a bit and say, I mean, I'm not sure if I don't know if that's something that I haven't tried to actually prove that, but the vast majority of times when, at least in probability and statistics, the things which are sums or integrals that we're interested in can be written as expectations. And even, in problems more generally in pure mathematics, combinatorics, and things which have nothing apparently to do with probability, I mean, they really don't have anything to do with probability, you can introduce a probability distribution and formulate a sum or some complicated thing that you're trying to compute as an expectation, and you can use sampling methods, and people do that. So approximations are necessitated by, let me say, intractable. Usually the problems which are intractable or which are difficult are sums or integrals, and these are typically expectations. Okay, so let's talk about some pros and cons of sampling methods, just very sort of generically. So some advantages of sampling methods in general. And here I'm thinking about Monte Carlo approximation, importance sampling, sequential importance sampling, Markov chain Monte Carlo, all these sorts of things. The big major advantage is that they are easy. They are super easy both to implement and to understand. And so especially, this is easy compared to exact inference or some deterministic approximation. So this is perhaps the single biggest reason why people use these sort of sampling methods, is because they're easy to do. And another thing, which sort of goes along with being easy, is that they're very general purpose. They're sort of a black box. You can just choose whatever super complicated model you want. I mean, it can just be some crazy model, and then you can pull out your sampling algorithm, and you can get samples, and you can do approximate inference and approximate statistics and all that stuff. So it's very general purpose. It's very, very widely applicable. Now, that's not to say that it necessarily does very well on all of those very complicated models, but it can be applied and usually has some asymptotic theoretical guarantees. But this leads us to the cons, and the first con is that, so the first pro is that it was easy, and the first con is that it's also easy. And in fact, it's too easy. It's so easy that it's overused. So it's often used inappropriately. Because sampling methods are so easy, and I was talking about how general purpose they were and all that, it's sort of used as a sort of cure-all elixir, or some sort of wonder tonic that you just pour over your problem and you instantly get valid results, and that's just simply not the case. So to the boy with a hammer, everything looks like a nail, and these methods are the ultimate hammer. So beware that if you really want for sampling methods to give you good guarantees of performance, you need to think a little bit about whether that is actually the case. Okay, another con is that sampling methods tend to be slow, especially compared with well, maybe not all exact methods, but deterministic approximations at least, sampling methods tend to be slower. You have to get lots and lots of samples, typically, in order to get a good estimate, a good approximation of the thing that you're trying to approximate. And one more thing, which is sort of, so this is sort of related to this. It's, the fact that it's slow um, may cause it to be inappropriate for given problems. And also somewhat related is that it can be difficult to get good samples. So getting, my pen went black. Getting good samples, let me put good in quotes, may be difficult. It may be inefficient to get good samples. And we'll talk about what I mean in a couple videos coming up, what good samples might mean. It doesn't necessarily have to be true samples from the actual probability distribution. Sometimes you can actually do better by not sampling directly from the actual probability distribution that your model comes from, or that your model defines. But choosing an alternate distribution that gives you good samples in some sense, it might still even be very difficult to do that, to get those, to actually draw those samples in an efficient way. And one more con I would like to mention is that it can be difficult to assess the performance of your method. Difficult. So this is one reason that leads to why it's often used inappropriately. Difficult to assess whether your sampling method is actually giving you a good approximation or not. So whenever you're making an approximation, you would like to know whether it's a good approximation. And one problem which can come up especially with, for example, Markov chain Monte Carlo methods, is that it can be very difficult to know whether you're actually getting a good approximation or not. Okay, so that was a general discussion of sampling methods and their pros and cons. And next, we'll start looking at some particular sampling methods.